Okay, so we're going to go ahead and do the RL circuit, which is a series circuit with a battery and an inductor. So we've got a battery minus plus, a resistor, and an inductor with the symbol L and the units of a Henry. Okay, so what we want to do is we want to set up the differential equation using a Kirchhoff loop rule. The first thing I'm going to do is I'm going to label the plus and minus ends of each of my circuit elements. We know a resistor is an energy user. So here, closer to the battery, it's going to start with higher energy and then lower energy after it uses some up. And then think about the inductor, what the inductor wants to do. Is it going to align itself with the battery, or is it going to oppose it? Of course, an inductor opposes the battery because the battery is forcing current through the inductor, which is creating a magnetic field. So the inductor is going to try to induce an EMF to put a magnetic field in the opposite direction. Okay? So as I go across my loop clockwise, both the resistor and the inductor are drops in current. So I can set up the Kirchhoff loop rule. It is the voltage gain of the battery, epsilon, minus the voltage drop across the resistor, minus the voltage drop across the inductor. But remember, the voltage on an inductor is just L di dt. Again, that is self-inductance based on the magnetic field that's created from the current going through the inductor. And again, the sum of all the voltages around the closed loop have to equal 0. So I'm going to go ahead and solve this thing so that I get an expression for the derivative. The derivative that I see here is a first-order derivative of current with respect to time. So I'm going to go ahead and move that over to the other side of the equation. So epsilon minus r is equal to L di dt. I'm going to divide both sides by L, the inductance, to get the derivative by itself. So 1 over L, epsilon minus I r is equal to di dt. Okay, great. So if the question on the AP exam says, write but do not solve a first-order differential equation, I'm done right here. This is a first-order differential equation. And then the next step might be to solve to get I as a function of t. Okay? So what I'm going to do is I'm going to manipulate this thing a little bit so that I can get something that looks like the integral on my equation sheet, which is integral of 1 over x plus a is equal to the natural log of x plus a. So I see my one variable here, current. What I want to do is I want to get it by itself with no coefficient, and I also want it to be positive so that it can look like that. Okay? So the first thing I'm going to do is factor out a negative r on the left side. So I get negative r over L times, well, I factored out a negative to make the current positive, so that's I, but it's going to make the epsilon carry a negative now in front of it. And I factored out a negative r, so that leaves me here with an epsilon over r. And that's all equal to the derivative with respect to time. Okay, so now I need to attach each variable to the small factor, and the only variable that I have is right here, the current. So I'm going to have to get this whole term, I minus epsilon over r, over with di, and I'm going to also multiply both sides by dt. So minus r over L dt is equal to di over I minus epsilon over r. And I'm ready to integrate because each variable is attached to the correct small factor. Time is easy. I know that the integration bounds are going to be starting at t equals 0 when I flip the switch or when I connect the circuit, and ending at some time t, sometime later. And now I need to match that up with current. Well, the current at time equals 0 is going to be 0. There's none. And then sometime later, the current will just be I as a function of time. Whatever time later, I can figure out the value of that current. Okay? The left side is a pretty easy integral. The integral of a constant dt is just minus r over L times t. The integral on the right side is a little bit more challenging, but again, I got it to look like this integral that's on your equation sheet, right here, right? So I know the integral is just going to be the natural log of I minus epsilon over r, evaluated from 0 to I as a function of time. Don't forget those integration bounds. Over here on the right side, 0 is going to contribute something. So we need to make sure that we don't forget that step. So minus R over L T. I'm going to go ahead and put my integration bounds in when I when I evaluate with just current. I get ln of I minus epsilon over R minus, and then when I evaluate it with 0, I do get a term here. It's ln of minus epsilon over R. I lost my negative there. So minus epsilon over R. Remember, when you subtract natural logs, it's the same thing as the natural log of the quotient. So I have minus R over L times T is equal to the natural log of the quotient I minus epsilon over R all over negative epsilon over R. Right? I need to get I need to get my function I out of the natural log. So I'm going to EFI both sides. I take e to the power of. So on the left side, it's e to the minus R over L T. And on the right side, I've gotten rid of my natural log. So that is I minus epsilon over R all over negative epsilon over R. So I'm going to go ahead and solve this for current. I'm going to multiply both sides by minus epsilon over R. E to the minus R over L T is equal to I minus epsilon over R. And I just need to get rid of that constant term right there, the minus epsilon over R, by adding epsilon over R to both sides. Epsilon R minus epsilon over R e to the minus R over L T is equal to my current as a function of time. Great. The last thing I'm going to do, because I expected this to be an exponential approach. When we talked about it qualitatively, I said that the inductor would be able to shut down the current at the beginning, but then it's going to approach some maximum value as the inductor just begins to act like a wire at the end. So I factor out an epsilon over R, and I see that now this is an exponential approach of minus R over L times T. But what is this guy right here, epsilon over R? That's the maximum current, and it looks like the current if there was just a resistor and nothing else in the system or in series with the battery. Okay, so this guy would look like this: current as a function of time. It's approaching some value of epsilon over R. It starts at 0 and it's an exponential approach. Okay. The other thing I want to point out right here: remember that this function is 1 minus e to the minus t over tau, where tau is in the denominator. So that means our tau, our time constant for the LR circuit, is just L over R. Good. Excellent. So we're going to move on later and do the LC. This is Mr. R signing out and reminding you that when we have two loops with no current, they give no flux.